Hi. Okay, so last topic for the semester, so last sort of major topic for the semester, so always very exciting to feel like, you're sort of bringing it all to a conclusion. Okay, so graph theory. It's been my experience that most folks in the class, everybody in the class, will have had a good background in at least some of the material that we're covering. So the idea of covering it really is to bring together different people's backgrounds. Sometimes people have seen one thing, some people have seen another thing, and so we try to wrap it up and make sure everybody has the same vocabulary and the same basic ideas, leaving the class going, I hope, going into 208, where I hope I see you. Okay, so as an introduction, I'm just going to remind a person what graphs are and motivate a little bit where they come from. Graphs are really the vocabulary that we will use to express problems in computer science. Okay, so the bridges of Königsberg is the first example, and Königsberg is a city in Prussia. On the far eastern side of Germany, basically the far western side of Poland, it's set on both sides of a river. You can't really see the picture all that well, but the river splits into two parts here. Can you see the two parts around an island? And there are some bridges over that island, and the problem was to find a walk through the city that would cross each bridge once and only once. So we need a better picture than the one we have. So in 1735, Euler was asked that question, and he made the following observation. He said, here's the island, G. It's a German word. I'm not going to attempt it. And the land on the north is called S. The land on the south is called R. And this part over here, this is actually another island, is called K. And again, I'm not going to attempt to to pronounce the German word for those areas. And there are two bridges between S and G. There are two bridges between G and R. And there is a bridge each between S, G, and R, and K. So Euler observed that this part here has nothing to do with land. It's just a spot that you are on when you're not on a bridge. Likewise here, and likewise here. So he shrunk the land to a single point or a circle large enough to label it, and he called it, and we call this a graph. A graph is nodes. There are four of them here, connected by edges. There are what 1, 2, 3, 4, 5, 6, 7 edges. So Euler then observed that if you're going to walk around, the city, for example, you might start at S and then go to G and then go to R and then come back to G. That if you're going to go over each bridge, not twice, only once, then for every bridge in, there's got to be a matching bridge out. That is to say, that except possibly for the landmass that you're on at the start and the landmass that you end up in, each landmass has to have an even number of bridges touching it, or incident on it is the technical jargon. And when you look at the picture, that's just not so. Here, odd number of bridges, odd number of bridges, odd number of bridges, odd number of bridges. So because there are more than two landmasses with an odd number of bridges, it's not possible. Okay, beautiful argument, and this idea of expressing relationships by making connections between those land masses, between the S and the G and the K, etc. That's the central part of graph theory. Okay, next up, 1857. So William Rowan Hamilton gave a proof of some algebraic fact, and in order to prove the algebraic fact, he had to find a path around a Platonic solid, visiting each vertex exactly once and traversing no edge twice. A friend of his suggested that the idea might make some money as a game. It's in some way analogous to Rubik's Cube. So they marketed one, and the players had to visit the vertices of a dodecahedron. And there you see the dodecahedron, and those are little like cork like from a wine bottle, and they're labeled with numbers. And then the number one was supposed to be, it's called around the world. So the number one was supposed to be Paris, and the number two was London, and the number three was this sort of stuff. And so you were supposed to find a way around the world, visiting each city exactly once. And there's an example of a tour that takes you around the dodecahedron. You're allowed to skip some edges, unlike the Euler problem. Here you're allowed to skip some edges, but you're not allowed to skip any circles. You have to go through every vertex, and you have to return back to where you started from. So that was two examples of graphs, and we're going to start on a third example of a graph. This is England, and you don't have to read it. It's probably too small for you to read. But these are the counties of England. You might recognize some of them from if you've read, for example, Sherlock Holmes. So Suffolk, Norfolk, Essex, kind of thing. Sussex, Hampshire, Dorset, this Devon kind of stuff. So all those counties in England, the historically important counties of England. Okay. In 1852, there was a man who was coloring the counties of England, and of course, he had like colored pencils or something. Of course, he wanted that if counties were adjacent, then they were not the same color. Otherwise, how could you tell them apart? And he noticed that in fact he could do the map with a maximum of 4 colors. And in fact, any map he tried to draw could be done with a maximum of 4 colors. So he asked his brother, who was actually going to see some mathematical lectures by Augustus de Morgan, and the brother, after class, went up to Augustus de Morgan and said, "Hey, my brother has this question, and I wonder if you know how to prove it." And Augustus de Morgan did not, and the problem, got asked around among mathematical community, and it's so easy to state, and it sure seems like it ought to be doable. Anyway, there was some history of a claim that some people believed for a while was actually right. Turns out not to be right. So the question is, do 4 colors suffice to color any map of this kind? And that's called the 4-color theorem. And over the next 120 years, a number of proofs were given that all turned out to be false. Basically, the idea is that you have a planar map, a map in the plane, and the map has some contiguous regions. I've drawn here 5 regions, and this green region here is next to this beige region. The yellow region over here is next to the green region, but the purple is not next to the green. So there are 1, 2, 3, 4, 5 different countries. And I colored it with 4 colors. Now I was able to color 2 of the regions beige. Those are different regions. I was able to color 2 of the regions beige because they don't share a border. And furthermore, a 1-point border doesn't count. You can't like all come together in a single point like a pie and say I have 400 regions all touching. That doesn't count. So the idea here, what does this have to do with graphs? And the idea is very, very straightforward. You draw a little node there for each region. And if 2 regions share a border, a non-trivial border, then you connect them with an edge. And now you've turned this coloring of regions question into a question of graphs. And now instead we talk about coloring the nodes of the graph. Is it possible to color the nodes of this graph with 3 colors? Is it possible to color the nodes of this graph with 5 colors in such a way that if 2 nodes are connected, they are not the same color? These 2 nodes are allowed to be the same color because they're not connected. Okay, so that's called a graph coloring problem. 1976, year I graduated high school. A long time ago. 1976, Apple and Haken proved the theorem. They did a by-hand analysis, which took hundreds of pages, and they reduced the problem to 1,936 separate cases. And then they wrote a program to prove, to go through those 1,936 cases. And they went down to the committee. In those days, computers were so rare. When I graduated high school, computers were so rare that the University of Illinois had a committee, and you had to go down and they begged for time on the computer. Could we have time between 2 o'clock in the morning and 4 o'clock in the morning to run this program? And the university, sort of had the wisdom to allow them the time, and they cracked it. The program ran, and it worked, and it showed the 4-color theorem in what I think a person can regard as an ugly way, but nonetheless it's shown, which is better than not shown. This was historically the first use of a computer to prove a serious theorem in some essential way. So there's the 2 of them. I think that right up there is Haken, and that's Apple, I think. Okay, so we've given a couple of examples of sort of the language of graphs. So now we're going to get down to some actual definitions. Okay, graph consists of nodes, some of which are connected by edges. So a graph is a pair of sets, n, e. I usually use script G for graph just because. the things in N are called nodes or vertices, and the things in E are called edges. Each edge is a set of two distinct nodes, which are called the ends of the edge. The order of the graph is the number of nodes. It looks like absolute value bars because we always use absolute value bars to denote the size of something. And here's an example of two different graphs here. So each of these two graphs is capital G is n comma e, with n is n0, n1, n2, n3. So you see n0, n1, n2, n3. And over here you see n0, n1, n2, n3. And you also see that the edges are n0, n1. There it is, n0, n1. See how it's a set, so there's no particular order. n1, n2, n1, n2. N1, N3, N1, there it is, N1, N3, and N2, N3, N2, N3, and you can go through the other one. So these two graphs are in fact, although they look a little different, these two graphs are in fact equal. Graphs are about the nodes and the connections. They're not about how you drew them on the screen. So what if you want to rotate, none of that matters. Okay? So strictly speaking, for the definition of graph, the two graphs are equal if they have the same nodes and the same edges. And recall that a binary relation is a set of ordered pairs, so a graph is a way of thinking about binary relations. We'll talk about that more, not today, but soon enough. And we're going to use graphs to model a variety of things, so we'll see some variance on this definition. When we need to distinguish it from other cases, the graph that's on this page, the definition called a simple graph, because it's the thing that we build other examples out of. So again, some vocabulary words. I'm sorry, there's a lot of vocabulary, but it's all necessary. So we say that an edge is incident on its end nodes. Two nodes are adjacent if there's an edge between them. And sometimes in a graph you can have an edge connecting a node to itself. That's called a loop. A graph with multiple edges connecting some nodes is called a multigraph. So there's some variations already on simple graphs. You could have a loop, you could have a multigraph. It all depends on what it is you want to model. So this is a simple example. So I live over here in Jericho. And these are the various towns that when I go for a jog, sometimes I take these routes. So for example, sometimes I just run within Jericho. So I never leave the town of Jericho. I run from Jericho to itself, so that I modeled that with a loop. I can jog from Jericho to Essex, and there's really two different ways that I can go, Route 15 or Route 117, not that it matters, but I can go via Route 15 or I can go via Route 117, and I want to express that. So in order to express that, I put in two different edges. So what you put in just depends on what it is you want to say. Likewise, there's two ways for me to get to Richmond, and sometimes I go one way and come back the other, so I need to have two different ways. Sometimes I go through Essex Junction to get over to Colchester, kind of thing. So what you put in for your model, there are different kinds of graphs, and it all just depends on what it is that you want to talk about. Okay, so time for some less sort of fanciful examples. So here's this is called K4, and this one's called K5. And what characterizes what's happening here is that there are 4 nodes, and I've connected every possibility. Here there are 5 nodes, and I've connected every possibility. When you've put in every possible edge, then you say that it's a complete graph. K4, K stands for complete. K4 is a complete graph with 4 nodes, and K5 is a complete graph with 5 nodes. It's no more complicated than that. Here's another example of a graph. This is called the Peterson graph, very widely used because a lot of times when you're going to, is it possible that in all cases when you take a node, a Peterson graph is a good one to check against because it's often used as counterexamples. Okay, so famous graph, Peterson graph it's called. There are 10 nodes, and I'm not going to count the edges, but 10 nodes and a number of edges. Okay, here's the 3 cube. Right there, the 3 cube. So it's supposed to be the case that that node right there is the nearest to us. That is, if you look very closely, that's the node nearest to us, and then that's the node furthest from us, but it doesn't actually matter. That's the 2 cube, usually known as the square, and the 1 cube, usually known as a line segment. Here's another example of a graph that you can see I got off the internet. This is some constellations in the Eastern tradition. And one thing that's interesting about this particular graph is that some of these things are not connected to others of these things. So Ursa Major and Ursa Minor are not connected. If you're standing here in Ursa Major, there's no way to go edge, 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 and end up in Ursa Minor. You just can't. It's as though I had written my jogging map, and on my jogging map I included London. I mean, you just can't get there. You just can't. Never mind whether you could jog. You just can't. There's no connection. So these are called connected components. So graphs can have different parts. An example of a complicated graph, just I wanted to throw one up here. This is the wiring diagram for a Honda motorcycle. So all kinds of things are connected to all kinds of other things. You see the little dots there when things are meant to be connected. And sometimes when lines cross and there is no dot, it's meant to be not connected. The point is that graphs can be very complicated. And analyzing graphs can be very hard. And one more example here, this is the chemical structure of methanol, the chemical structure of wood alcohol. And so clearly you can view some aspects of methanol on a just purely graph level, that these three H's are connected to that one C, and this one H is connected to that O. So there are some purely graph aspects of the structure of the molecule. And finally, here's Manhattan, the original plan for Manhattan, and you can see, of course, that down at the bottom, the old town, the old city, it was, grew up sort of willy-nilly, helter-skelter, but when they were making a plan, then they made it all linear all the way up to the top there. Okay, so a lot of nodes, a lot of edges. And then finally, the last just sort of random graph I'm going to give you is The Simpsons. I got this family tree of The Simpsons, and I'm obviously not going to go through it, but you can see, all your favorite characters down there is Bart down there, and Homer, and Marge, and Maggie, and anyway, Anyway, so all the Simpsons, there's Grandpa, all the Simpsons. And so a big tree. So again, graphs can be very complicated, can have a lot of things to say. A family tree is going to have some constraints on it that something that isn't a family tree won't, and etc. Okay, so we're talking about a variety of different kinds of graphs, and emphasizing here that a person puts in different things, layers things over a simple graph when they have something to say. That's all. If what you want to say is that it's possible to have loops, then you need to include loops. If loops are not something you're modeling, then don't include them. Okay, directed graph, digraph. The edges have a direction. So you can imagine, for example, one-way streets in a map of a city, but there are a lot of other times in which you have a direction. Imagine, for example, that you're trying to write down here how you assemble a bicycle. And so you have to do this before that. So you put an arrow that says you can't go from B back to A, you have to go from A to B, kind of stuff. So a directed graph has edges that have a direction in that each edge has a start node and an end node. And one way to formalize directed edges is that the elements of E are not sets instead, but are ordered pairs. And here's an example of my lowly place in the organization of St. Michael's College. Here's me down here at the bottom in lowercase letters. And in some sense, I report to the math chair. In some sense, the math chair reports to the VPAA and also to the dean. And in some sense, those two august individuals report to the president. But anyway, it's a directed graph for the obvious reason. Okay, now there are some things that you can say about graphs, but if you want to say something about every possible graph, there isn't all that much you can say, because graphs come in a tremendous variety. But one thing you can say is the following. The degree of a node is the number of edges incident on that node. The degree of a node is the number of edges incident on that node. So for example, the math chair here has 3 different edges incident on it. The president has 2 edges incident on it. You can, in a directed graph, talk about the in degree and the out degree, but at the moment I'm just talking about degree. And if an edge has a loop from the node to itself, you got to count that loop twice. It has 2 loops, and it makes a total of 4. So the sum of the degrees of all the nodes is equal to twice the number of edges. Let's have a look. Oh, went the wrong way. There we go. there are 1, 2, 3, 4, 5 edges. Right? 1, 2, 3, 4, 5 edges. This node has degree 1, so that's 1 so far. This node has degree 3, so that's 4 so far. This node has degree 2, so that's 6 so far. I'm out of fingers. This node has degree 2, so that's 8 so far. This node has degree 2, so that's 10 so far. 5 edges, total of degree 10. 5 edges, total, when you add up from all the nodes, degree 10. And the explanation is very simple, is that every edge gets counted twice, once for each end of the edge. So the sum of the degrees of all the nodes, if you add up the degrees of all the nodes, you're counting each edge twice, once for one end of each edge and once for the other end of each edge. Okay, a small observation, but you'll be surprised. Sometimes these things turn out to be exactly what you need. And with that, I can make the corollary that again, if you want a statement to apply to every possible graph, there's a tremendous variety of graphs. So any statement that can apply to every possible graph is probably going to be a small observation, but worthwhile. Okay, so give me a finite undirected graph. Find the number of nodes that have an odd degree. So it might have degree 1, it might have degree 3, it might have degree 5, it might have degree 7. So degree 7, remember, is that there are 7 edges leaving it. And that includes that if you have a loop, that counts as 2 edges. So degree 1, degree 5, degree 3, degree 7, degree 153, whatever is the odd number, don't care. So look at all the nodes that have an odd degree. How many of them are there? And the answer is there's got to be an even number of them. So again, look at all the nodes that have odd degree. How many? The answer is there has to be an even number of them. It could be 0, but 2 or 4 or 6 or 8. So why is that? Well, we know from the theorem that if you add up the degree of all the nodes, you have to get an even number because it's twice something. It's twice the number of edges. Throw away the nodes with even degree. What's left are the nodes with odd degree. When you throw away the nodes with even degree, you've thrown away an even number because it's all you throw away the first node with an even degree, you've thrown away an even number. Throw away the second node with an even degree, you've thrown away an even number. Keep going until you've thrown away all the nodes with even degree. You've thrown away in total an even number. But the total was still even because you took an even minus an even, so the total is still even. You're adding up a bunch of odd numbers and getting an even result. There's only one way to have that happen. You add up a bunch of odd numbers and get an even result. You must have added an even number of them. So 1 plus 3 makes an even number. 1 plus 3 plus 5 does not. So again, a small observation, but comes up surprisingly often. So restated in sort of maximally confusing way, in any set of people, some of them have shaken the hands of an odd number of people. They may have shaken the hand of 1 person, or 3 people, or 5 people. Separate out all of those odd shakers. So you imagine a room, and you say to everybody, you let people mingle for 10 minutes, and you say, okay, how many hands have you shaken? If you've shaken an odd number of hands, you go to the left. If you've shaken an even number of hands, you go to the right. On the left, all the odd shakers, there's an even number of them. Okay, so again, working through a variety of different kinds of graphs, just really trying to get used to and make sure everybody has the same vocabulary. So bipartite graphs is an example of a kind of graph. What you see here is that I've broken the graph into 2 categories. I wrote capital letters and small letters just to make it easy to tell the 2 categories. And so Ann likes Adam, so I have capital A and lower a. I connected them with an edge because there's the like relationship between them. Beth likes Adam. Beth likes Adam. Beth also likes Carl, and etc. A simple graph is called bipartite. If the set of nodes can be split into disjoint parts, in this case the top line and the bottom line, if the set of nodes can be split into disjoint parts such that every edge connects a node in one part to a node in the other. So here, every edge connects top to bottom. They connect it in all kinds of crazy ways, but they connect top to bottom. Never are 2 tops connected, never are 2 bottoms connected. So a simple graph is bipartite if we can assign each node a color, red or blue, that is from a set of two colors, so that adjacent nodes are different colors. So C and B would be different colors, B and D would be different colors, etc. And it might seem like silly nonsense, but trying to keep talking about modeling here. So it may seem like silly nonsense, but it isn't silly nonsense. You can imagine, for example, listing all the students at St. Michael's at the top, all the courses at St. Michael's at the bottom, and we'll connect with an edge if a student is going to take a course. So of course, students don't take students. Of course they don't. Of course, courses don't take courses. Obviously, that's not true. So only do we have edges from top to bottom. That's the only thing we have. Okay, so bipartite graph come up a lot because you often have this matching circumstance. Trying to match students up with courses. Trying to match courses up with rooms, for example. Trying to match workers with jobs. Trying to match airplane crews with airplanes that they can fly. This kind of stuff. Bipartite graphs come up an awful lot. Okay, last slide for the day. Sort of a lot of vocabulary, and that can make it hard to follow. But I do anticipate that a person has already seen a lot of this in other courses, especially beginning programming courses. Okay, so the graph G hat is a subgraph of G. If the vertices are a subset and the edges are a subset, might be equal, but could be a proper subset. Now, I want you to note that starting with the mistake you can make here, starting with the graph G and removing some nodes doesn't yield a new graph. You have to also remove the relevant edges. Okay, so if I tried to go back to the bipartite example on the previous slide, I can't just erase A at the top. There's some edges hanging there that are not connected to anything. So what you're looking at is that you remove the nodes, and if you remove the sort of associated edges, well then what you get is the subgraph induced by the new set of nodes. Okay, and so that has to do with the structure of a graph. You're trying to take subset of a graph. So I'm making graphs smaller. We can make graphs bigger by taking the union of two graphs. So the union of two graphs is, instead of taking things out, you put things in. The union of G union H is the graph formed by taking the union of the set of nodes and the union of the set of vertices. So that G would be a subgraph of G union H, H would be a subgraph of G union H. Okay, so what we've seen then is, in addition to just the raw definition of graph, is we've seen some variations on that definition. And the point I'm trying to emphasize is that those variations you're going to see them in or not in, depending on what it is that you want to model. If you want to model a circumstance where you have students matching courses, then you want a bipartite graph. So that's the kind of graph you look at. If you want to model the my place in the St. Michael's organization, very low down. If you want to model my place in the St. Michael's organization, then you want to somehow have a structure of reports to, reports to, reports to. Okay. Okay, very good. So that's a beginning. And now next time we'll talk about paths in graphs. Okay, great.